Hello again. I'll continue with symbolic execution. If you remember in the last class, I had introduced symbolic execution to you, shown you a couple of examples and given you an overview of the technique. What I'm going to do now is continue with it. We'll look at the third example. So here is another program. This time, this program has a loop, and the idea is to understand how symbolic execution works on programs that have loops. So here is a piece of code. It's named as test me infinite, INF, short for infinite. Don't worry too much about the name. Let's understand what the program does. It has an internal variable called sum, which is an integer type, initially assigned to 0. Then it takes as another variable which is of type integer called capital N. How does it take it as? It takes it as input. It takes it as symbolic input. Which means what? You take it as a symbolic input, eventually substitute it with concrete value. And then the program has the piece of code. What does that code do? It has a while loop which says as long as the input that you have read of integer type is an input greater than 0, you keep adding it to the sum that you have collected till now and take the next in. If you happen to get an input that is less than or equal to 0, then this while loop gets aborted. Otherwise, this program, this while loop will run forever as long as somebody gives it positive inputs. So that's why this is called infinite. So this program has a problem. The problem is this program, the loop in the program could be non-terminating, and whether the loop terminates or not is fully based on the next input that the user gives. I want to show or flag this as a potential error in the program because it has an input statement inside the while loop. It can go on running as long as the condition of the while loop passes. What is the condition of the while loop? Condition of the while loop just says that the input that you have read just now, is it greater than 0 or not? So this program will go on running as long as somebody gives it positive inputs. I want to use symbolic testing to identify this as a problem with the program and tell the user that there is a problem. How will I do that? If you remember the steps of symbolic testing, what are the steps? Instead of giving concrete values to inputs, give symbolic values. For every internal variable, collect a symbolic expression, which is basically substitute the value of the input that comes in the expression with its symbolic value. Collect path constraints that tell you about each of the decision statements in the program. If the decision statements were simple if statements like the ones we saw earlier, there would have been no problems. Here, the decision statement in this program is a while statement, and it's a while statement which says n greater than 0. Now you could go by the previous time's example and say that the path constraint will be symbolic value of n greater than 0. But then just that as the path constraint doesn't tell you when this while loop is going to stop. You also have to give a negation of the path constraint. For every path constraint that you encounter as a decision statement or if for a while, you have to be able to give its negation also. What is negation of n greater than or 0? That is n less than or equal to 0. And how will I give it as a path constraint for this? Because it's a while loop, it has to run for one or more iterations. In fact, it runs as long as n is greater than 0, and when n is less than or equal to 0, it will stop running. Is that clear? That's what I specify in a path constraint. This is what I was trying to explain it to you. I'll go through this slide now. The loop in the example that we are seeing in this slide, example 3, has infinite number of execution paths, as I told you, where each execution path is a sequence of arbitrary number of trues followed by a false when it stops, or it can go on as a sequence of infinite number of trues. So the path constraint for a loop with a sequence of n trues where n is unknown, it's completely dependent, small n is unknown, it's completely dependent on the user. This while loop, let's say the user tries to give positive values of n first 3 times, fourth input that he gives is negative, the while loop will stop. Let's say the user tries to give positive values of n 100 times, 101st input he gives as negative, then after 100 iterations the while loop will stop. User could decide to give first 10,000 values as positive and then 10,001th value as negative, the while loop will run till then. User continuously gives positive values while loop will go on running. That's what is captured here. It says that there is some n whose value I don't know, and the path constraint says that till that value of n, that is for I is equal to 1 to small n, all the numbers that I get, capital Ni's, are greater than 0, and after this n, there is a n plus 1th value which is less than or equal to 0. This n may or may not exist. If this n does not exist means what? For no n, n plus 1 is less than or equal to 0 means for every n, ni will be greater than 0, which means the while loop can go on executing. That it captures that succinctly. And what will happen after, at each step of the execution, sum gets assigned to sum plus that value of ni, and the new input of ni is read. That's what is represented here. Sigma, which represented the symbolic state, which I had explained in the previous lecture, looks like this. There are two variables in the program, capital N and sum. Capital N will stop when the program go at the end of execution, when the program gets n plus 1. And what will sum be? Sum will be the summation of all the inputs that you have read till now. So in general, by using this example, what have we learnt? If I am doing symbolic execution of a code that contains loops or recursion I have not shown you, but that holds for recursion also, it might result in an infinite number of paths if the termination condition for the loop is such that it is also symbolic. For these kind of things, usually what people do is that they put a timeout. They wait and then they say, no, there is a problem with the program. I am doing this for too long. Then they go and look at it and abort. Or they limit the number of paths, loop iterations, or the exploration depth. So this is how you collect symbolic constraints for loops. So symbolic constraints for loop will have a particular number of iterations where the path constraint for the loop turns out to be true. And then after the specified number of iterations, the path constraint will be false. In this case, why I showed you this example directly is that in this case, the next iteration of the loop is dependent on the structure of the loop. This is a particularly problematic case. So I don't know whether I can stop it after a finite number of iterations or not. Or I don't know whether that small n will exist or not. That's the case, then symbolic execution may or may not terminate, and that truly reflects the problem in this program also, because concrete execution of this program also may or may not terminate. It will not terminate if a user continuously gives positive values. It will terminate if the user eventually gives a 0 or a negative value. So now, what is the biggest problem with symbolic execution? The biggest problem with when does symbolic execution end? When we are able to solve the path constraint and collect a set of test cases. In the case of this example, this was the path constraint to be solved. What is this path constraint solving means? Find some n such that you give the first n values as numbers that are positive and n plus 1th value as numbers that is less than or equal to 0. We can always find like this. As I told you, the small n could be 3, 10, 100, whatever. It will be satisfied. What was the path constraint for this one? For this piece of program that was given here, right? 3 path constraints was there. One is the first if statement negating to be false. And the second one was first and second if statement both were true. First if statement was true, second if statement was false. All the cases, these path constraints have to be automatically solved. These were small programs that I told you for illustrative purposes, but for large program, imagine a large program with 10,000 lines of code, several different if statements, and you symbolically execute, you collect a large constraint. So you have to give it to a constraint solver, expect the constraint solver to be able to solve the path constraint for you. As I told you, solving path constraints means looking at satisfiability problem in logic. If you remember in the lecture on logic that I did towards the first half of the course, where before we began logic-based testing, I had told you that satisfiability problem is a hard problem. Even for an elementary logic like propositional logic, there is no known polynomial time algorithm for solving satisfiability, or in other words, satisfiability problem for this is NP complete. We are not even talking about propositional logic, we are talking about predicate logic, which means if there are variables that are of type integers that are not always Boolean. Satisfiability problem for predicate logic or first order logic is undecidable, which means there is no algorithm to do satisfiability. But there are lots of so-called constraint solvers which use exclusively designed heuristic-based techniques to do satisfiability. I'll point you to references, a couple of them towards the end of this course. So suppose you get a path constraint and you are able to solve it using a constraint solver, then well and good, you can do symbolic execution and drive the program towards the desired paths that you need or cover all the paths in the program. But let's say you are able to not solve the path constraint and get a collection of inputs, then there is a problem. Symbolic execution may not be useful. Why will you not be able to solve a path constraint? Because there could be functions like f of x is less than or equal to 0.5 and you may not have the code corresponding to f of x. Or let's say in a programming language like C, if you include the maths.h library, you can write things like if log x is less than 0.005, then you do something. Things like log may not be efficiently computable by certain constraint solvers. So there could be several different reasons why arbitrary functions and predicates cannot be computed. So if one such problem exists and constraint solver says I am not able to solve, then symbolic execution is not particularly feasible for that. In fact, this is considered to be one of the key disadvantages of using symbolic testing. So to summarize all the disadvantages of symbolic testing, the PC or the path constraint, as I told you just now, generated during symbolic execution may not be solvable by any constraint solver, then you're stuck. You can never get test cases. Why will it not be solvable? Because the underlying program could use a function whose code is not available. Then how will you know what f of x computes? This is very common when you're using web applications and all. You might use functions whose code is not available. And as I told you, many real life programs which have a few million lines of code have several different program paths. So as you go on symbolically executing a program, there could be several decision statements and you might end up collecting a really long path constraint, which is very difficult to solve. It's so long, it has so many variables that several constraint solvers might not find it feasible to be able to solve, in which case exploring all paths may not be feasible. So in fact, symbolic execution was first introduced in the year 1976, quite old, almost 40 years from now. But then it has come into use only in the past 10 years. It was dormant mainly because of these disadvantages. Recently, people have devised a lot of techniques from 2005 onwards where some of the disadvantages that I've listed here can be overcome. So one of the techniques that people have introduced that helps us to overcome the disadvantages of symbolic testing is what is called concolic testing. Concolic testing is short form for concrete plus symbolic. Concolic. That's how they have coined that term. It means that you, instead of keeping a symbolic value alone, which we do in symbolic testing, you keep the concrete value along with the symbolic value. We will learn one particular concolic testing technique called DART, Directed Automated Random Testing. I will teach that to you in the next few lectures. We will see how it overcomes several of the disadvantages that we have listed of symbolic testing in this slide. Concolic testing, as I told you, keeps the concrete state along with the symbolic state. Concrete state is the normal notion of a state of a program. If you remember in the last lecture, if you'd let me go back in my slides for a minute, we had this sum program. If you remember this program that calculated the sum, a concrete state would be value of A is 1, B is 3, C is 5, X is 4, Y is 8, Z is 9. After statement number 4, concrete state would be X4, Y8, Z9, A1, B3, C5. After symbolic execution in line number 4, X would be alpha 1 plus alpha 2, symbolic expression. Y would be alpha 2 plus alpha 3, another symbolic expression. There would be another symbolic expression for Z. The inputs A, B and C would have gotten symbolic values. So now I'll move forward to concrete testing. So concrete testing or concolic testing keeps concrete state, as I just told you, which means it keeps concrete values, actual values, and it will keep a symbolic state. It will keep the symbolic values and the expressions. Why does it keep both? The difference will be obvious very soon, I'll tell you. And what it tries to do is that by keeping track of both, it has the convenience of moving back and forth. So that's what it does. So if I have to take that other example that I told you in the last class, again, let me go back to show you that example. This was that example. If you remember, it took two inputs x and y, did z is twice of y, and then it said is z is equal to x. If it is, then is x plus y greater than 10, then there is an error. This was the program. Here, if you remember, the symbolic expression was all these, right? I'll show you that slide also. Symbolic state was x is x naught, y is y naught, z is 2y naught. These were the path constraints. X naught is equal to 2y naught, x naught was not equal to 2y naught, and this was after the second if statement was executed. What we will now do is look at concolic statement. So concolic execution, what will it do? It will keep a concrete state. How will it keep a concrete state? Here is one particular way of keeping a concrete state. It will give a random input to the program. Let's say x is equal to 22, y is equal to 7, or any other choice. What it will do is that it will start executing the program. Once it starts executing the program, x is equal to 22, y is equal to 7. Go back to the code of the program. For this concrete input, this condition, will it pass? It will not pass. So this condition will go as failed, which means the second if statement will not be evaluated. So that's what is written here. The concrete execution on this input will make the program take the else branch. Symbolic execution will generate saying that, by the way, the program took an else branch because x naught is not equal to 2y naught. What will concolic testing now do is that it says, okay, the program took the negation of this, right? I will negate this condition to see what the program will do if it takes the other one. So it will negate this, which means it will say x naught, give inputs x and y such that x naught equal to 2y naught. Here is one such input, x is 2, y is 1. Now what will it do? This, it will go to the next statement in the program. The next statement in the program, concolic testing will say, okay, I did this, which was already my path condition. By the way, I encountered one more if statement, which was this. And this is the part of the if statement that is satisfied by this test case. Now it will say, okay, it took one particular branch, I'll take this condition, negate it to make it take the other branch. So when it negates it, it will get this condition. X naught equal to 2y naught, that's not the predicate under focus, it will keep it as it is. This was the predicate under focus. Here it was x naught less than or equal to 2y naught. I'll say x naught is greater than y naught plus 10. Sorry, there's a typographical error. Here it should be 10. Please read it as 10. So now it will correctly get the test input x is equal to 13, y is equal to 5, and it will hit the error statement in the program. So this is how concolic execution works. This is just meant to be an introductory example. I will explain concolic execution, in fact this particular technique of concolic execution called DART, in detail to you. So what does concolic testing do? This is, you can think of this as a concise summary of concolic testing. It has a program that it wants to test. What it will first do, it will generate a random test input to the program. It will execute the program on the random test input. The program will take certain program paths. As the program takes certain program paths, it will parallelly symbolically execute the program. When it symbolically executes the program, it will collect constraints which said, okay, the program encountered the first if statement. The first if statement encountered in the program for this random input turned out to be true. So it will keep that constraint over symbolic variables. And then it will move on. Let's say program encountered a second if statement. Second if statement on this run of the program turned out to be false. So it will take the constraint corresponding to the first if statement, negate the constraint corresponding to the second if statement, and these two. It will keep collecting path constraints like this. Now this represents one concrete execution of a program on that random input and a whole set of path constraints. Now what concolic testing will do is that this path constraint is an AND of several different path constraints, right? So it will systematically negate each clause in it and then try to see what the new execution of the program does. And for that, it will use a constraint solver to get concrete values of inputs, and it will repeat this till all the execution paths are done. So here is another example of concolic testing. So this is a different function. So it says there is a function f which says x is an integer variable. Like the earlier thing, it just did 2 star x. There is a function h which says takes 2 arguments x and y and returns an integer. It has 2 if statements. First one, if x is not equal to y, then it goes to the second statement. Second says if f of x, which is this f up here, equal to x plus 10, then you abort. Abort means you stop, there is an error in the program, you return 0. If you notice, that is very similar to the earlier one, just a small piece of difference from the earlier example that we had. Now the problem is, this is the place that I want to reach. Using concolic testing, how will I do? I'll first randomly generate 2 inputs. Let's say x is 26, y is 34. Any randomly generated inputs. Then 2 predicates are there. X naught is not equal to y naught, which I know because in this random input that's true. And then 2x naught is not equal to x naught plus 10. That's what this means, right? Because f of x does 2x and x plus 10 is captured here. So both these are taken. Path constraint looks like this. I take the second one, negate it, then I'll get something that will reach this statement. So this will be true and this will be true. I would have reached the error. That's how concrete testing works. Is that clear? I'll explain it using an example and look at the general techniques of Dart and so on in the next lecture. Before I stop, I would like to tell you that there are modern constraint solvers. They will give you some references when I begin the next lectures. And now there are several popular symbolic testing techniques, tools that exist. There's a tool called Qt, Symbolic Testing Unit, Concolic Unit Testing Engine for C, developed by University of Illinois. There's Qt for Java, which is again developed by University of Illinois at Urbana-Champaign. There is Specs, which is available for .NET code as a part of Microsoft Visual Studio. There's Sage and so on. And several other companies have developed symbolic testing techniques tools. I will give you the URLs of all these and some constraint solvers when I begin the next lecture. In the next lecture, what we are going to see is this Dart technique in detail, directed automated random testing. I'll tell you what that is and how concolic testing works on that. Thank you.